Now you see that in this case, in particular, you are having N type of wafer and P type of wells. So this is a PMOS. There you have the whole P type of wafer and N type of well. This is called NMOS. That is how you create the NMOS and PMOS on the same P type wafer. Did you got the idea that how NMOS and PMOS are created on the same silicon wafer? Anyone, if you have any doubt, please ask. Please unmute yourself and ask the question. Did you understand that the wafer, the whole wafer is of P type, but I'm creating PMOS as well as NMOS on the same wafer? How?
यस
Right?
सर, बट पीमोस को ज्यादा एरिया नहीं घेरेगा फिर?
Absolutely. अगर आप P टाइप वेफर के ऊपर PMOS बनाएंगे तो एरिया ज्यादा लेगा. जब आप केडेंस के अंदर लेआउट डिजाइन करते हैं तो देयर इज अ जनरल क्वेश्चन कि NMOS एरिया कम ले रहा है, PMOS एरिया ज्यादा ले रहा है. देयर यू हैव द आंसर. बिकॉज आपको P टाइप वेफर के ऊपर ही एक N टाइप पहले वेल बनाना है, उसमें दो P टाइप वेल बनाने हैं, उससे आपको एक PMOS का स्ट्रक्चर बनाना है. आप कभी केडेंस के ऊपर लेआउट बनाएंगे लेबोरेटरी में तो आप देखेंगे कि PMOS जो है वो ज्यादा स्पेस लेता है बजाय कि NMOS से. उसका रीजन यही है. Any other question? This was a good question. Right? So shall we move forward? अभी हम लोगों ने क्या किया है? What we have done is that we have understood how PMOS and NMOS is created. Now let us connect with uh, how these NMOS and PMOS structures are um, used in parallel to what we learned yesterday. For example, you see this NMOS structure very carefully. आप इस NMOS structure को देख रहे हैं. कल हमने पढ़ा था that we have a P-type substrate. उस P-type substrate के ऊपर you have a layer of SiO2 and then you have a gate. हम लोगों ने तब ये कहा था कि गेट से अगर आप नेगेटिव वोल्टेज देंगे, इफ यू प्रोवाइड नेगेटिव वोल्टेज फ्रॉम गेट, यहां से होल्स अट्रैक्ट होंगे और यहां पर आकर सारे के सारे इकट्ठे हो जाएंगे. द होल्स विल एक्यूमुलेट ओवर हेयर. बिकॉज द होल्स विल एक्यूमुलेट ओवर हेयर, दैट इज व्हाई दिस प्रोसेस वाज कॉल्ड एक्यूमुलेशन. आप यहां से इस नेगेटिव वोल्टेज को व्हेन यू विल कन्वर्ट इट टू अ पॉजिटिव वोल्टेज which is a small positive voltage, you will see that this here is a positive voltage, holes are also positively charged. So positive and positive same charges repel each other, and you will say because the voltage is very small. So what this voltage will do is this voltage will, here you have SiO2 and here you have gate. Now this voltage will repel these charges. This will repel in accordance with the strength of the voltage. Now this voltage will repel them and will push them to this place. Right? Pushing them to this place will make this part empty. Means there is a case of depletion. So from accumulation, you reach to depletion. Now, what happens when you apply more stronger positive voltage over here? The more stronger positive voltage, this will repel these positive charges more. These positive charges will go further away from this surface, but this voltage is very strong. that it will start pulling up the minority negative carriers from here. And the minority, because positive will attract negative, you will see the electrons traveling to the surface. From where we started, the positive charges accumulating to the surface, where we reached negative charges attaching to the surface. So the whole process get inverted, reversed. So that is why this process is called inversion. Please understand that in NMOS, this is the only process of channel formation. The voltage which is just enough to have the electrons over here on the surface, वो voltage जो मिनिमम चाहिए इलेक्ट्रॉन्स को सरफेस तक लाने के लिए, that voltage is called threshold voltage. This threshold voltage depends on several factors. We will see this in our coming lectures. लेकिन MOSFET में आपको कुछ चीजें और ध्यान में रखनी होंगी जब हम इसमें और थोड़ा सा आगे परस्यू करेंगे. फॉर एग्जाम्पल, this was the structure of NMOS. There you have two wells of N, and here you have P type. And in two N structures, there you have source, there you have drain, and there with SiO2 you have gate. आप लोगों ने सबने कैपेसिटर पढ़ा होगा. व्हाट इज अ कैपेसिटर? कैपेसिटर के को अगर आप कुछ सप्लाई दे दो यहां से, तो क्या होता है कि आप सप्लाई इस तरफ दोगे and some charge start appearing on this plate, and in between the capacitor you may have air as a dielectric or some insulator as a dielectric, right? This impacts the capacitance. Now what happens is कि आपके पास जब ये कैपेसिटेंस यहां से क्रिएट होती है, तो आप ये समझो कि यहां पर गेट है और यहां पर आपके पास सेमीकंडक्टर है. ये मेटल, ये सेमीकंडक्टर, और बीच में SiO2 का इंसुलेटर. तो समझो दिस ऑल्सो वर्क एज ए कैपेसिटर. ऊपर आपके पास ये गेट है, ऐसे ऐसे देखो, ऊपर आपके पास ये गेट है मेटल वाला, और नीचे भी आपके पास एक कंडक्टिंग, यहां पर आपके पास एक लेयर है इलेक्ट्रॉन्स की, ये कंडक्टिंग मेटल है, राइट? ये पी टाइप सिलिकॉन है. सो बीच में आपके पास देयर इज अ लेयर ऑफ SiO2. So now this becomes a capacitor. Got the point? That is why we call that MOSFET. Sometimes is called, people call it as MOSCAP, MOSFET capacitor, from where the capacitance comes inside the MOSFET. And the second thing is that the MOSFET also work as a resistor. कैसे काम करता है रेजिस्टेंस की तरह? When you give some voltage from gate, you will start watching some current. And what we have studied, that when you give certain voltage and you start getting some current, then there you have the formula V is equals to IR. So this resistance is there, definitely there. But the point is, in Ohm's law, this resistance is linear, because MOSFET is a device of semiconductor, and in semiconductors you have non-linear resistance, right? So I think I have created some of the basics for you which are required for you to understand the today's lecture, with which we'll move forward. See, in this lecture we will be talking about a few valence band and conduction band and energy band structure which is given in Kang and Lebesgue EC, which are very difficult to understand, but I have made it simplified for you. अगर आपको कहीं पर समझ नहीं आएगा तो प्लीज डू आस्क मी. अभी इसमें देखिए, यहाँ पर यू हैव द गेट वोल्टेज, यहाँ पर you have the substrate voltage, there you have a semiconductor silicon, and there you have the oxide, right? ये वही structure है जिस structure पे just we have worked upon. In this structure, one need to understand that in particular, when you apply some voltage through gate, यहाँ पर कुछ इलेक्ट्रॉन्स जो है नेगेटिव इलेक्ट्रॉन्स जो नेगेटिवली चार्ज कैरियर्स हैं इन्वर्जन के बाद यहाँ पर आ जाएंगे और ये मॉसफेट कंडक्टिंग हो जाएगा. नाउ let us see this energy band diagram of MOS system. Remember, this is the energy band diagram of MOS system, not MOSFET. Got the point? There is a difference between the MOS system and the MOSFET, right? So now please see this. This is a metal. In metal, yes, in metal, you will see that there is a valence band and here is a conduction band. When electron move from valence band to conduction band, we used to say that the current is flowing. It is working as a conductor. Now in metal, valence band and conduction band are overlapped. When valence band and conduction band are overlapped, it means electron को तो valence band से conduction band में जाने की जरूरत ही नहीं है, वो तो already conduction band में है. That is why, because electron is already in the conduction band, that is why metals are always conductive in nature. Any device in which electron can move to conduction band will become conductive in nature. Now you see in insulator, which is called oxide, we are talking about MOS system. This is metal oxide semiconductor. In oxide, you will see that this is the conduction band EC, this is the valence band. There is a huge energy gap between valence band and conduction band, which means whatever energy you give to electrons in the valence band, आप इलेक्ट्रॉन को वैलेंस बैंड में कितना भी एनर्जी दे दो, इलेक्ट्रॉन कंडक्शन बैंड में जा ही नहीं सकता. इसका मतलब अगर एक इंसुलेटर आप उसको कितना भी वोल्टेज दे दो, कितना भी पुश करो, it will never go to the conduction band. So it means it will never conduct. So that is the property of an oxide. That says that this is if you see in metal, there is a term which is given as EFM, and this is E naught. EFM is the Fermi level, right? And this is called the work function of the metal. Please understand these terms, Q, phi, M. This is work function of metal, which is 4.1 electron volts, which is very small. If you see the work function of insulator, see 8 electron volts. It is very high, right? The oxide band gap 8 electron volt is very high. That is why it acts as a perfect insulator. And if we talk about the semiconductors, see in this case, in semiconductors, we have this 4.15 electron volt, where the work function in metal was 4.1 electron volt. It means it is slightly higher than the metals, and the band gap, which is from conduction band to the valence band, valence band to the conduction band is only 1.1 electron volt. Here it is 8 electron volt, 8 times lesser. It means that if you give very small voltage over here and you give some push to the electron, it will move to the conduction band. So what was the difference? The difference was in metal, electron was already in conduction band. In insulator, electron will never move to conduction band. And in semiconductor, if you give some voltage, electron can move to conduction band. And if you see this EI, this is the intrinsic level. It is called intrinsic energy level. and this EFP is Fermi level in semiconductor. And here you see that this Q phi FP, this represents the energy needed to remove the electrons from silicon. See this arrow, please note this arrow. This energy is required to send the electron from silicon to depletion, and when more energy is given, then electron from depletion to inversion, this 1.1 electron volt is traveled. That is the difference. So what we have concluded from all this is that in metal you can always conduct because electrons are in conduction band. In insulators, electron can never reach to conduction band, and in semiconductors, if you apply some voltage, it can move to conduction band. What is this QX silicon? This is called silicon electron affinity. Silicon electron affinity. So what is the silicon electron affinity? Silicon electron affinity is the energy difference between this vacuum level and the conduction band. Okay, so what are the takeaways from this slide? Takeaway is the MOSFET, this MOS system has the structure like a capacitor. This oxide, which is an insulator, the band gap is very high. The metal work function is very low, and this metal always works as a conductor. And this Fermi level, when I talk about this Fermi level, this EFP, this actually works. This is very important. When we'll study this Fermi potential graphs, then this will come into the picture. मैं आपको ये सब क्यों बता रहा हूँ, ये इसलिए बता रहा हूँ कि जब आप कैन की बुक पढ़ोगे तो उसके अंदर ये पार्ट बहुत डिस्क्रिप्टिव दिया हुआ है, और जब आप लोग एक हायर लेवल पे प्रोजेक्ट्स बनाने लगोगे तब आपको इसकी जरूरत महसूस होगी, बिकॉज प्रोजेक्ट बनाना, आउटपुट लेना इज नो बिग डील, उसको एनालाइज करना, उसमें से कुछ निकालना कि इसको ऐसे इंप्रूव किया जा सकता है बिकॉज सिलिकॉन का ये कैरेक्टर रहा होगा, दैट इज मोर इंपॉर्टेंट. इसीलिए इतना पुश देके मैं आपको ये समझा रहा हूं. इसको अगर नहीं समझोगे तो सिर्फ एक सुपरफिशियली प्रोजेक्ट्स बनाते रहोगे, उसके अंदर नहीं घुस पाओगे, एनालिसिस नहीं कर पाएंगे हम लोग कभी. दैट इज वाई इसको समझना बहुत जरूरी है. Now this diagram, it is a very prominent diagram in, if you see the scan book, many a times people skip this diagram, but this is very important. Let us decrypt it one by one. What it says, first of all, what is EI, then what is EC, what is EFP, what is EV, what is EFM, this is QVG. These are the different words that we need to decode. What is this EFM? This EFM is metal Fermi level, right? See, metal has a Fermi level, semiconductor has a Fermi level. Oxide do not have any Fermi level. It is an insulator, right? Now the point is, मेटल एक ऐसी चीज है जिसके अंदर ऑलरेडी इलेक्ट्रॉन कंडक्शन बैंड में है. सेमीकंडक्टर एक ऐसी चीज है जिसमें आप इलेक्ट्रॉन को कंडक्शन बैंड में भेज सकते हो, लेकिन आपके पास ऑक्साइड एक ऐसी चीज है जिसमें कंडक्शन बैंड में पहुंच ही नहीं सकते. अब आपको, जब आप किसी मॉसफेट के अंदर ऊपर से सिलिकॉन डाइऑक्साइड के ऊपर से आप कुछ एनर्जी दोगे, तो आपको इसके नीचे यहां पर इलेक्ट्रॉन इकट्ठा करना है सिलिकॉन में, राइट? कैपेसिटर की तरह काम करवाना है. तो आपने यहां से जब एनर्जी दी तो यहां कितनी एनर्जी पहुंची? दिस इज द क्वेश्चन. डिड यू गॉट माय पॉइंट? If you give some energy from gate, how much energy reaches to your semiconductor? This is very important to understand, and this is called aligning of energy levels between metal and semiconductor. I repeat, that is called aligning of um, energy levels between metal and semiconductor. Now, please see that these lines are very straight and these lines are curved. Why these are straight? Why these are curved? Because silicon metal के साथ align करने की कोशिश कर रहा है. Silicon is trying to align with metal. That is why those get bent. Now, when three materials are combined, Fermi level must become equal everywhere. अगर Fermi level equal नहीं होंगे तो कैसे चलेगा? You see that there is a word which is called equilibrium. A system to be to do not give you shock should be in equilibrium, right? And when you connect a metal with a semiconductor, the atoms and ions between themselves put in a state of equilibrium by adjusting their energy bands. That is why when you create two different semiconductors, two different MOSFETs, even if you create with the same composition, they never become the same. Why they do not become the same? Because their energy levels do not align in a very equal manner. That is why practically two MOSFETs are not same. Now, you please see this EFM represent metal Fermi line on the left side, and in the oxide region there are no free carriers, right? That is because there is no free carrier, so there is no Fermi level. We'll come to this is very easy to explain, that you have some VG0. आपने गेट पर 0 वोल्ट दिया हुआ है, ये आपके पास लाइन है 0 गेट वोल्टेज की, लेकिन जैसे ही आप यहाँ पर गेट पर कुछ वोल्टेज देते हो, वो फर्मी लेवल पर आ जाता है और आपका मेटल जो है वो कंडक्ट करना शुरू कर देता है. बट व्हाट इज द प्रॉब्लम विद सेमीकंडक्टर? सेमीकंडक्टर के अंदर ये बेंड्स क्यों है? सेमीकंडक्टर के अंदर ये बेंड्स इसलिए हैं because there are three curves. This EC relates to conduction band, this EV relates to valence band, EI relates to intrinsic level, right? See, क्योंकि Zoom में मीटिंग का ऑप्शन 40 मिनट का है, so that is why I am closing this meeting as of now. आप इसी लिंक पर प्लीज दोबारा ज्वाइन कर लीजिए सब लोग. I request all of you please join on the same link again so that we can continue this.